Okay, let's unpack this. You know how sometimes you ask a big language model a question and it just, well, it makes things up.
Uh-huh.
Or it sounds smart, but its knowledge feels, I don't know, a little out of date.
Yeah, that happens. You're definitely not alone there.
Well, today we're diving deep into a fascinating solution to that problem. It's called Retrieval-Augmented Generation, or RA for short.
Right. And what's truly powerful about RAG, I think, is how it acts like this dynamic, always up-to-date library for these models.
The dynamic library, I like that.
Yeah, it allows them to pull in current factual information basically on demand. And that significantly reduces those, hallucinations and keeps the responses really fresh and accurate.
Exactly. And for this deep dive, we've got an incredible foundation. It's a comprehensive systematic literature review of RA by Andrew Brown, Mohammed Roman, and Barry Devereaux, published just this year. This review covers a massive 128 highly cited studies from 2020 all the way up to May 2025.
And this isn't just like a random collection of papers. It's very meticulously structured. It uses the PRISMA 2020 framework, which gives a really transparent and cohesive look at the entire RAG landscape.
Okay.
It's designed to give both researchers and engineers insights into the latest techniques, how we measure success, and, the big challenges still ahead.
So our mission today for you is to distill the absolute most important insights from this huge body of work.
Yeah.
We'll break down what RAG is at its core, explore the innovative ways it's being built, how we actually measure if it's working, and what major hurdles it still faces. Get ready to connect some serious dots, because this really is where the rubber meets the road.
Let's do it.
So what does this all actually mean for you and how these systems work? At its heart, RAG is about giving a generative language model. Think of it like a purely creative writer, a powerful partner, a neural retriever, which acts like an incredibly fast and accurate research librarian.
That's a perfect analogy, actually. The generative model, it's brilliant at crafting fluent text, but it's prone to factual errors when it needs external knowledge.
Right, the making things up part.
Exactly.
Yeah.
And traditional search systems, well, they can find information, but they can't then compose new, nuanced text from it. Our RAG elegantly combines both. It provides that strong factual grounding without sacrificing fluency.
Oh.
By letting the generative model query an external knowledge base in real time, right when it's generating the answer.
Okay, that makes sense. This whole field really took off when Meta AI introduced R back in 2020, right?
That's right. And it has diversified incredibly rapidly since then.
Right. But before we get into all the cool new innovations, let's talk about the foundational stuff, the plumbing of RAG, how we prepare and find that external knowledge.
Absolutely. The first critical step is something called document chunking.
Chunking. Okay.
This is how we take large pieces of information, like, say, an entire article or even a book, and break them down into smaller, manageable units. Chunks the retriever can actually search through effectively.
And the review highlights just how much this seemingly simple step has evolved.
It was humorous.
Early ARG systems often used basic fixed-length segments, maybe 100 words or like 64 tokens. A token's basically a word or part of a word.
Right. And while that was easy to implement, that approach could accidentally cut right through a complete thought or sentence.
Oh, right. So you lose crucial context.
Precisely. It could, as the review puts it, bisect semantic units. So this immediately raises the question, how do you keep the information coherent?
Yeah.
Later research moved to what's called semantic boundary-aware splitting, meaning aligning those chunks with the inherent structure of the text, like breaking its sentence or paragraph boundaries. Makes sense, right?
Yeah, much smarter.
And even more advanced techniques look at hierarchical sections directly from PDFs. This is crucial because, as one study found, a simple pre-processing error could otherwise completely mess up the original document's meaning for something like a clinical chatbot.
Wow, okay. And I found this part fascinating. The rise of specialized chunking.
Tell me more.
Like, for source code, they chunk by functions. For legal documents, they might break cases into specific question, snippet, entity, answer pairs. Super specific.
Exactly. Tailored to the data. And then there's adaptive dynamic chunking, which tries to automatically figure out the optimal chunk size based on the specific query you ask it.
So it's not one size fits all.
Not at all. It's all about ensuring the right size piece of information is found. Not too big, not too small, just right.
Okay. So you've got your documents smartly chopped into these digestible chunks. The next big challenge for AG is, well, finding the relevant ones from potentially millions of billions of them.
Right. The retrieval part. The survey breaks this down into 5 main mechanisms.
Sure.
On one end, you have sparse term-based methods like BM25.
Yeah.
These are very efficient, very fast at finding exact word matches.
But they don't really understand meaning.
Exactly. They struggle with semantic understanding. Then there are dense retrievers like DPR, which are much smarter. They translate queries and documents into these numerical representations called vector embeddings.
Ah, vectors. Okay.
Right. This allows for semantic matching, meaning they can find concepts that are similar even if the exact words aren't used. And of course, hybrid approaches try to combine the best of both worlds.
Here's where it really starts to get clever, I thought. Some systems have these encoder-decoder query generators. They can actually reformulate your complex questions into better, more effective search queries, like rephrasing it for the search engine.
Yeah, like a smart assistant clarifying your question before searching. Other innovations include reclassification modules that reorder search results. They make sure the most useful information is right at the top, even if the initial search pulled back some noise.
And for really structured information.
For deep dives into that, there's graph retrieval. This can extract specific relevant subsections from complex knowledge graphs, giving you these explicit reasoning chains. It's very powerful for certain tasks.
Building on this, iterative frameworks are also popping up.
Right. This is where the language model's initial attempt at an answer can actually refine subsequent queries. It creates a kind of feedback loop.
Improving the reasoning over multiple steps.
Exactly. Significantly improves multi-step reasoning. The trade-off, though, is it does add a bit more time, more latency to the response.
That makes sense.
And we're also seeing highly specialized retrievers designed just for unique data, like code snippets or specific types of medical reports. It really highlights how tailored ARA needs to become for different applications.
So you've got your smart chunks and these clever ways to find them. But where do you actually store all this highly processed information so it can be quickly accessed? That's where vector databases come in, right?
Absolutely fundamental. Vector databases are key for RAG. They allow for incredibly fast similarity searches over those dense embeddings we just talked about.
How do they do that so fast?
They typically use techniques like approximate nearest neighbor or A&M. It lets them quickly find vectors that are conceptually close to your query without having to compare every single one. The key challenge always for these databases is balancing search accuracy with speed, latency, and how much memory they consume.
And what's really cool, I think, is how they've also developed specialized vector stores. You mentioned medical reports.
Yeah, exactly. Systems like RepoCoder are tailored specifically for code retrieval. Chroma is designed for biomedical concepts. It really shows how adaptable RAG needs to be, how the storage itself needs to fit the knowledge domain.
And getting the information into those vector spaces requires vector encoders, these models that do the translation.
That's right. These are the models that convert your text, or maybe even images later, into those numerical embeddings. They can be scarce, like that BM25 method we mentioned earlier, focusing on keywords.
Or dense.
Or dense, using deep learning models like BERT, Sentence BERT, or maybe proprietary APIs like OpenAI's text embedding at a 002. The choice of encoder is a really important trade-off. It impacts retrieval accuracy, how much computing power you need, and ultimately how well it understands the nuances of a specific domain.
Okay, so the review makes it pretty clear that RAG research isn't just about proving the basic concept works anymore. It's pushing boundaries now.
Absolutely.
It's about making these systems more adaptive, more controllable, inherently trustworthy, and also just incredibly efficient.
Right. Which brings us to this next section, which emphasizes what you might call the behind-the-scenes work, or maybe the unsung hero.
The pre- and post-retrieval plumbing.
Exactly. The crucial steps that happen before the main retrieval and after you've pulled back those initial results.
So on the pre-retrieval side, it's more than just simple chunking now. It's about structuring documents intelligently.
Yes, like aligning chunks with titles or tables within the document. It also involves enriching those chunks, maybe with AI-generated keywords to help shorten the searches later, or carefully curating the entire knowledge base, the corpus, to weed out potential wild hallucinations that might creep into domain-specific bots.
And there was a really important security point here, too.
The retriever, not necessarily the big language model, often acts as the outer security wall.
So defending that entry point is crucial.
Absolutely critical. Adding filters right there at the retrieval step is key for defense.
Okay, and post-retrieval, after the search.
That focuses on refining what you get back. Re-ranking the results is vital, making sure the best, most relevant passage appears first for the LLM.
And trimming the fat.
Right. Using tools like sentence-level selectors or creating fast extractive summaries. These cut down on the amount of text the language model needs to process. Saves on tokens, saves processing times, saves money, while hopefully still keeping the key facts intact.
Okay, my favorite detail here, though, was the idea that sometimes noise can be medicine.
Huh. Yeah, that's a counterintuitive one.
Yeah.
A few unrelated passages retrieved alongside the relevant ones can actually act as a kind of regularizer for the model.
And slightly improve factual scores. That's wild.
It is surprising. It also speaks to the importance of verifying early and fixing errors locally, using these small critic LMs, smaller specialized language models, to quickly flag if a problem is with the retrieval step or the generation step.
And then trigger only the necessary fix, not regenerate everything.
Exactly. Much more efficient.
Moving on, this next section really treats the prompt itself, what you actually type into the model, as a kind of living control panel for the whole RG system.
That's a great way to describe it. Because even subtle changes to the grounding guidance within the prompt can dramatically reduce hallucinations. The review mentions it having hallucinations in, like, conceptual math problems just by tweaking the prompt.
Wow. And for more structured tasks?
Using things like JSON or graph templates within the prompt can help enforce the output format you want, and it also reduces the model's cognitive overhead, makes its job easier.
And here's another real eye-opener for me. Letting the LLM itself expand or rewrite the user's initial question.
Yes, multi-query expansion. It can significantly boost recall, find more relevant stuff.
Like asking the question in a few different ways automatically.
Precisely. And some advanced systems, like Flare, even have these uncertainty-triggered systems.
Meaning?
They only send out a search query when the language model's token-level entropy spikes, which basically means the model is really unsure what word it should generate next.
So it doesn't search unless it really needs to.
Exactly. Avoids unnecessary trips to the knowledge base, saves time and resources.
Very efficient.
And if we connect this to the bigger picture, more sophisticated prompt styles, like React-style prompts, interleave steps like thought, action, observation, this allows the model to actively plan its tool calls, like making a search query, and revise its approach as it goes. It's almost like mimicking human problem solving.
So the clear takeaway here is that a good prompt policy often beats an architecture tweak.
That's what the review suggests. Treat your prompts like code. Version them. Test them. And RG systems become much more controllable, potentially cheaper, and safer too.
Okay, this next part is where RG seems to go from being just a one-off helper to like a true interactive partner.
The review calls it a decisive migration from the traditional retrieve-then-generate pipeline towards closed-loop systems.
Closed loop. What does that mean in practice?
It means the language models can now continually query external knowledge, they can inspect their own drafts, and revise both the context they retrieved and the answer they're generating. It's dynamic.
And those uncertainty triggers we just talked about are key here.
Absolutely. The model retrieves only when it genuinely feels it needs external information. We see this in systems like Self-RAG. It uses special reflection tokens that basically signal, I need to check this, or how good is this evidence I just found?
This is a huge leap, isn't it? The model can literally emit a search string as a token, like type out its own search query.
Yeah, exactly. You might see something like, search what's the capital of Australia, appear in the generation process.
Yeah.
And the system interprets that as a direct instruction. Go look that up, Nick.
It's like the model saying, hold on, I need to check my facts.
Precisely. We're also seeing iterative refinement with frameworks like chain of note.
Chain of note.
Yeah, where the LLM writes its own reading notes for the documents it retrieves, helps it understand reliability, compare sources, and further reduce hallucination.
And there are loops that even fix themselves.
Yes, verification-driven loops, like in a system called KLMV. They can enact automatic error rectification if a grounding fault is detected.
Meaning if the generated answer isn't actually supported by the facts it retrieved.
It can potentially identify that and fix itself.
Wow. What about feeding drafts back?
That's happening too. Generation-augmented loops feed intermediate drafts back to the retriever. This provides increasingly informative queries as the answer gets built up. It's like a detective refining their search as they uncover new clues.
And for really complex problems.
For those you see task decomposition or multi-hop retrieval, a big problem gets broken down into smaller sequential sub-problems, each potentially requiring a new search or a new piece of knowledge.
So the common lesson here seems to be that retrieval should be policy-driven. Only search when needed.
Right. Fire only under measured uncertainty, not just blanket searching for every query. And local revision fixing things efficiently prevents those prompt links from just exploding.
And fail-safes are important.
Crucial. Closed loops require fail-safes, like those lightweight critic LLMs we mentioned. This truly recasts RAG, moving it from just a search tool into a genuine interactive search companion.
Now, early RAG systems, as you said, were stateless. They treated every question like the first one.
Mm-hmm. No memory of the past.
But for things like personalized education or clinical care, you need context that builds up over time, right?
Absolutely. Which is why we're seeing the rise of memory-augmented RAG architectures.
So for short-term memory, like within one chat?
For that, you have conversational buffers. Something like LangChain's conversation buffer memory just retains the recent chat transcript. Helps a lot with follow-up questions in that session.
Okay, but what about longer-term user-specific memory?
That's the next step.
Mm-hmm.
There's an example of a hepatology assistant, a medical bot called Laversa. It smartly separates long-term documents, like patient history, from short-term conversational signals, and it keeps a dynamic slot just for recent queries.
And the benefit.
According to the study, this setup cuts hallucinations by about 25% and halves prompt length. Pretty significant.
Affluent.
Or you have concepts like the agentic brain, which logs every single perception, thought, action step it takes. This builds a really comprehensive memory for planning complex, multi-step tasks over time.
So this really shifts RAG from just answering the current question
to accompanying the user over time, becoming a persistent assistant.
But that must introduce new challenges.
Oh, absolutely. Big challenges around memory governance. Things like how long should you retain information, when should you delete it, maybe for privacy reasons, and addressing the problem of forgetting or dealing with stale memories that become outdated or incorrect. Lots to figure out there.
Okay, so if standard RAG is that smart research librarian, then agentic RAG is like the super librarian who can also, I don't know, cook, fix your car, plan your vacation.
Yeah, basically by intelligently calling the right tools for the job.
So this is about how an LLM can weave together all these different capabilities.
Exactly. Weaving together retrievers, memories, external APIs like weather or stock prices, calculators, even other LLMs into a single adaptive execution plan.
Can you give an example?
Sure. A system called MedRAG, a medical agent, orchestrates 5 distinct steps. It has a judger, a retriever, a re-ranker, a refiner, and finally a generator, each specialized. And the way these agents make decisions can range from static, predefined graphs or flowcharts to much more dynamic planning using those thought, action, observation tokens we talked about.
And memory here isn't just an add-on.
No, it's treated as a peer, an equal partner to retrieval in these agentic systems. This unlocks big benefits, like managing workflows that span many interactions, days, or even weeks. And it allows for gracefully falling back on alternative evidence if one tool or one source doesn't pan out.
But this sounds complex to manage.
It definitely brings challenges. Debugging these complex cascaded systems can be a nightmare. And figuring out credit assignment, like if something goes wrong, which tool or step was responsible, is really hard.
So we need better infrastructure.
Desperately. The review calls for things like vendor-neutral DSLs, domain-specific languages, to describe these tool graphs consistently, and for unified dashboards that report not just accuracy, but also latency, energy consumption, and privacy metrics all in one place.
Right. Because you might think with all these powerful models, cost doesn't matter as much anymore.
But it absolutely does.
The review has this great line. The first time a production team wired a 32K token model into its help desk bot, the GPU bill doubled overnight.
Ouch.
Yeah.
Every extra token, every symbol the model processes, burns memory, adds latency, and costs real money.
So researchers are actively chasing leaner recipes.
They have to be. We kick a system called XRAG, for instance. It manages to collapse each retrieved passage down into essentially one projected token.
One token per passage.
It's a clever projection technique, but the result is slashing GPU memory usage by 40% without losing factual accuracy in their tests.
That's impressive. Any other tricks?
Yeah, another one is PiperRAG, which, as the review says, refuses to wait. It cleverly pulls the text passages it needs from the slower CPU, while the faster GPU is already busy decoding the next part of the answer, overlapping the work.
Cutting down the waiting time.
Right. Cuts end-to-end latency by about a third in their experiments, and then there's RAG cache. This tries to intelligently guess which passages are likely to be needed again soon, maybe in a follow-up question. It pre-warms the cache.
And even starts speculative decoding.
Exactly. Based on those likely passages, These innovations clearly demonstrate that, frugality can coexist with accuracy in RAG. You can be smart about resources.
Okay, let's shift gears a bit. Imagine a disaster response chatbot. It doesn't just quote tweets about the situation, but it can also overlay that information onto live satellite imagery to give you a complete picture.
Right. That's the exciting promise of multimodal RAG, moving beyond just plain text to integrate different types of information: images, video, audio, tables.
So how does that work? Combining text and images, for example.
Well, systems like Murai connect specialized models. Maybe a vision transformer for understanding images, with a T5 encoder-decoder for text. The key trick is that both images and text are converted into the same numerical embedding space. They speak the same language, vector-wise.
So a text query can find a relevant image.
Exactly. It allows a prompt about, say, a mysterious lesion to fetch both the relevant radiology reports and the actual X-ray image, understanding them together.
And frameworks like LangChain are helping orchestrate this.
Yeah, they play a big role. They allow RAG systems to ingest data from HTML web pages, lecture videos, numerical data from sensors, all through interchangeable vector stores. This means potentially one single agent could answer complex questions that span different modalities, like asking about protein structures based on recent lab results.
But there must be challenges here too.
Oh, definitely. Big challenges remain. Current models, even sophisticated ones like those in the CLLP family, which are designed for image-text understanding, might still struggle to really grasp information presented in tables or maybe code snippets embedded within text.
And privacy, especially with medical images.
Huge concern. Establishing consistent, reliable privacy controls for sensitive modalities like medical scans is still largely an unsolved problem. Standardization is lacking. This is a absolutely critical area for future work to make multimodal RAG truly dependable and trustworthy in real-world applications.
Okay, so we've covered all this innovation, the components, the different approaches, but how do you actually know if your RAG system is working well? Is it giving good answers? Is it reliable?
That's the million-dollar question, right?
Yeah.
Evaluation. And it's much more than just getting a single accuracy number. You really need a comprehensive suite of measures, as the review calls it.
A suite. Okay, what's in it?
The evaluation landscape for R is typically grouped into three broad types. First, you have automated metrics. These are the most common. Second, human judge metrics, absolutely critical for the qualitative aspects. And third, an emerging pillar, LM as judge approaches.
Okay, let's break those down. Automated generation metrics first. How good is the text it writes?
Right. You start with standard text metrics, like accuracy or exact match. Is the answer strictly correct, word for word? Then there are classic measures borrowed from machine translation, like BLU and Rouge. They look at inogram overlap, how many phrases match a reference answer.
But those can miss the meaning sometimes, right?
They absolutely can. An answer could mean the same thing, but use different words, and Blue Rouge might score it poorly. This is where more advanced metrics like BERT score come in. Instead of just looking at exact words, BERT score measures semantic similarity. It compares the contextual embeddings we talked about earlier.
So it captures meaning better.
Much better. You also have measures for the modder's confidence and fluency, like perplexity. And specialized metrics are popping up for things like the diversity of answers, or crucially, how well the answer is factually supported or grounded by the retrieved documents.
Okay, so that's the generation part. What about the retrieval part? Did it find the right stuff?
Exactly. Automated retrieval metrics measure how well the retriever component does its job. Key measures include things like precision at K and recall at K. Precision at K tells you, of the top K documents it retrieved, how many were actually relevant.
And recall at K.
Recall at K asks, of all the relevant documents that exist in the database, how many did we find in the top K? It's about coverage.
Got it.
Are there others?
Oh, yes. Other crucial retrieval metrics reward the placement of relevant documents. Mean average precision, or MAP at K, gives higher scores for placing relevant documents earlier in the search results list. Mean reciprocal rank, MRR, at K, focuses specifically on how quickly the very first relevant document is found. Was it the top result, second, 10th?
And NDCG.
Normalized discounted cumulative gain, NDCG at K, is sophisticated. It accounts for graded relevance, meaning some retrieved documents might be highly relevant, others only partially. It rewards ranking the best ones highest. And hit at K just tells you if at least one relevant document was found in the top K. Simple but useful.
Okay, are there other automated metrics besides generation and retrieval accuracy? Yes, definitely. Researchers also look hard at computational efficiency, measuring on things like overall latency, how fast is the system, response time, throughput. For robustness, a really key metric is hallucination rate. Simply, what's the frequency of fabricated or completely made-up content? Needs to be low, obviously.
And rejection rate.
That measures the system's ability to gracefully say, I don't know, or refuse to answer when its knowledge is truly insufficient or it lacks confidence. That's often better than hallucinating.
What about bias?
Good point. They examine contextual bias, checking if the model blindly adopts incorrect assumptions or biases present in the retrieved context, even if that context is misleading. And of course, for specific applications, there are task-specific metrics, like cited for evaluating how good generated image captions are, or Passet K for code generation.
Passet K?
Yeah, it essentially checks if the code the model generated actually compiles and passes a set of predefined automated tests, a very practical measure.
Okay, automated metrics are great for scale, but they can't capture everything. What about human judgment?
Absolutely indispensable. The review is very clear on this. No matter how many fancy automated scores you have, human evaluation remains indispensable. This is where human experts, or sometimes crowd raters, step in. They check for actual correctness, relevance, and crucially, things that are hard for machines: hallucination and groundedness.
How do they check groundedness?
They distinguish between content that's completely fabricated versus information that's synthesized incorrectly from the retrieved facts, or maybe even contains false citations pointing to a document that doesn't actually support the claim. Humans are good at spotting that nuance.
What else do humans look for?
They assess factual correctness overall, consistency within the answer and with the source, comprehensiveness didn't answer the whole question, and just general overall quality from a human reader's perspective. And importantly, from the end user standpoint, you need to measure things like user satisfaction, system usability, often using standard scales like SUS, and technology acceptance. Will people actually use this thing? Do they trust it?
Okay, that makes sense. Now, the third pillar you mentioned was LLM as judge, using AI to judge AI.
Exactly. This is a really cool, relatively new and emerging trend. Using powerful large language models like GPT-4 to act as automated judges themselves. They can be prompted to assess correctness, overall quality, sentiment, coherence, fluency, even safety, often at a much larger scale and lower cost than human evaluators.
Can they really be as good as humans?
They're getting surprisingly good. These LLM as judge approaches can provide what's called LLM verified accuracy. They're particularly useful for flagging answers that are semantically correct. They mean the right thing but might be phrased very differently from a single reference answer, which might confuse simpler metrics. Frameworks like GEVAL specifically use LLMs to score things like coherence, consistency, and fluency, and studies show these scores often correlate quite strongly with human judgments.
So putting it all together, what does this mean for someone evaluating a RAG-G system in practice?
It means you can't rely on just one number. A truly balanced and rigorous evaluation combines those efficient automated scores with the irreplaceable, nuanced insights from human judgment, and increasingly leverages the scalable capabilities of LLM as judge methods to get a deep, comprehensive picture.
Makes sense. A multifaceted approach.
Exactly.
Now, despite all these amazing innovations and the rapid progress we've discussed, the review is also quite clear that RAG is still up against some pretty stubborn obstacles, things that need to be overcome for it to be truly widespread and dependable.
That's right. And these challenges often form an interlocking system. They're related and can compound each other.
Okay, like what? What's the first big one?
First, there are significant computational and resource trade-offs. We touched on this.
Deep.
While those dynamic queries and iterative loops we talked about drastically improve relevance and answer quality, they significantly increase the actual wall clock latency, how long you wait for an answer, and the memory footprint, the amount of computing resource needed. Lighter alternatives can reduce cost, but they often sacrifice how specific or accurate they are for a particular niche domain. It's a constant balancing act.
Okay, trade-offs. What's next?
Noise, heterogeneity, and multimodal alignment. Basically, your R pipeline is only as good as the information you feed it, right?
Garbage in, garbage out.
Pretty much. And those inputs can be incredibly noisy, inconsistent, or formatted differently. This is especially true with multimodal data, where you can get weird effects like semantic bleeding.
Semantic bleeding.
Yeah, an example from the review was irrelevant visual regions in a medical scan accidentally influencing the text similarity score, leading the system to retrieve the wrong reports because of some visual noise.
Yikes. Okay, what else?
Another major hurdle is domain shift, dataset alignment, and generalization. A RAG model that performs brilliantly with medical papers from PubMed might just completely fall flat when you suddenly give it legal documents.
unless you retrain it extensively.
Exactly, which is costly and time-consuming. Plus, a huge issue is that stale or erroneous material in the knowledge base propagates directly into answers. And that creates a really high-stakes liability in critical fields like finance and medicine, where an outdated or wrong fact can have serious consequences.
And it's sensitive. Small changes have big effects.
Incredibly sensitive. The review notes how subtle things like simply changing the chunk size you use or adjusting the number of document K to return from the retriever can cause accuracy scores to swing by double-digit margins.
Wow. Double digits just from tweaking parameters.
It really highlights the fragility sometimes and the need for careful tuning and robust evaluation.
Okay, what about errors cascading through the system?
That's another big one. Modular pipelines and error cascades.
In
these multi-step RG systems, if a retrieved passage is misranked or maybe just plain wrong in an early stage,
it messes up everything downstream.
It can irreversibly bias the language model's final answer. And in those memory-augmented pipelines we discussed, cached errors are re-retrieved in later turns, which just compounds the issues and makes them really hard to track down and fix.
Nightmare. And finally, constraints from the LLMs themselves.
Right. Large language model constraints and safety risks. First, the practical stuff. Commercial LLM APIs, the ones most people use, come with per-token fees and usage caps. Powerful models can get very expensive very quickly.
And context windows.
Fixed context windows, the amount of information the LLM can look at simultaneously can sometimes truncate important evidence, forcing the model to generate an answer based on incomplete information.
And the big safety risks remain.
Absolutely. Bias, toxicity, and hallucinations remain endemic, as the review states bluntly. Cleverly crafted adversarial prompts can still bypass existing safety guardrails. And any lapses, any mistakes are especially hazardous in medicine and other high-risk domains.
So connecting this all together, the review points to security as maybe the most critical challenge.
It really emphasizes security threats in retrieval-augmented generation, because the retrieval corpus itself, that external knowledge base, becomes a new attack surface.
An attack surface? Huh.
Researchers have shown that corpus poisoning backdoors can be created by attackers tampering with even less than 0.1% of the documents in the knowledge base.
Less than 0.1%. Even just one bad passage.
Sometimes, yes. Just one carefully crafted malicious passage can be enough to subtly steer the model's generation towards a desired outcome or make it violate its safety policies.
And it doesn't have to be obviously toxic.
Not at all. Attackers can craft passages that subtly bias the generated output without containing any overtly toxic or hateful language, making them very hard to detect.
What other kinds of attacks?
There are also demonstrated data exfiltration and privacy attacks, where LLMs can be tricked or coerced into copying sensitive private data verbatim from the retrieved context it was given.
Like leaking private user information stored in the knowledge base.
Exactly. And then you have jailbreak and policy evasion triggers.
How do those work?
Attackers can inject adversarial content, maybe hidden instructions, into documents that the retriever faithfully finds and surfaces to the LLM, because the retriever thinks it's relevant content. This effectively bypasses the normal safety guardrails that might be applied to the user's direct prompt, because the malicious instruction comes from the trusted, retrieved context.
And current defenses aren't great.
Often ineffective, unfortunately. The problem is that many current defenses, like simple perplexity filters or trying to rephrase user queries, don't work well, because these poison queries or malicious documents can be designed to cluster very tightly in the embedding space with legitimate content. The system fundamentally trusts the retrieved ground truth, even when that ground truth has been deliberately compromised. It's a really tough problem.
So, given all these challenges, what does this mean for the future? Where does RAG need to go?
The review emphasizes that true progress really hinges on co-design. We can't solve these problems in isolation.
Co-designing what?
Co-designing the algorithms, the infrastructure, and the evaluation methods together. We need things like latency-aware scheduling for those complex pipelines. We need new benchmarks that jointly score not just accuracy, but also robustness and security. And we need models that are balanced by having an adaptive retrieval depth, retrieving more or less information based on the need and the risks.
Okay. Phew. That was definitely a deep dive. We've really unpacked retrieval-augmented generation all the way from its basic building blocks to these cutting-edge innovations, and importantly, the critical challenges it still faces.
We really have. And we've truly seen a clear evolution, haven't we? From that basic retrieve then generate idea to these much more sophisticated modular policy-driven architectures. We're seeing hybrid retrieval, graph-aware indexing, even those uncertainty-triggered loops.
All leading to better recall, finding more relevant stuff, without just flooding the language model with useless information.
Exactly. And it's remarkable how these closed loops and those lightweight critic models are transforming retrieval. It's not just a static one-time pre-processing step anymore.
Right. It's becoming an ongoing conversation between the retriever and the generator,
allowing for things like real-time verification during generation and that deeply personalized memory we talked about. Plus, all those efficiency tricks are encouraging.
Yeah, they show that being frugal with resources, managing those costs, doesn't have to mean sacrificing rigor or accuracy. Frugality can coexist with accuracy.
But as we just discussed, important gaps definitely remain. Current evaluations often don't properly link accuracy with the real-world costs and latency. That's a big disconnect.
And systems still struggle to generalize robustly when you shift them to a new domain or different type of data. They can be brittle.
Very brittle sometimes. And crucially, defenses against that retrieval side poisoning and those prompt and context attacks, they're still pretty immature. A lot of work needed there.
So looking ahead, what's next for RAG? According to this comprehensive review, what are the key directions the field needs to take?
It gives us three really clear directions, three main calls to action. First, develop holistic benchmarks. These aren't just about accuracy scores anymore. They need to measure and report crucial factors like retrieval latency, the energy consumption, and quantifiable privacy guarantees altogether.
Okay, holistic benchmarks.
Second, treat retrieval strategy as a resource allocation problem. Think about it economically. Design policies for when and how much to retrieve that. Intelligently respect budgets, time budgets, token budgets, compute budgets.
Be smarter about spending resources. Got it. And third,
define open, vendor-agnostic interfaces. We need standard ways to connect RIG systems to diverse knowledge sources, not just text, but graphs, tables, images, real-time data streams. Standard interfaces would let practitioners easily swap in new retrievers or new knowledge sources without rebuilding everything.
Making it more modular and flexible.
Exactly. Fostering innovation.
So, if we connect this all to the bigger picture, what's the ultimate goal?
I think the review puts it beautifully. By tackling these challenges and dependencies together, future RAG systems won't just retrieve knowledge. They will reason over it, they'll quote it accurately, they'll budget for its use, and maybe most importantly, when the index lies, when the retrieved information is wrong or malicious, they will know how to walk away. They'll have the wisdom to distrust bad information.
Wow. A truly provocative thought to leave everyone with. Imagine a future where AI isn't just smart, but actually wise enough to know when it doesn't know or when it's being misled.
That's the goal.
That's all for this deep dive. We really hope you feel far more informed and ready to explore this fascinating, rapidly evolving field of RAG further.